Hi, I'm Marco, and I will tell you about the work I did with Andrea, Eric, and Francesca, learning a formula of interpretability to learn interpretable formulas. Nowadays, we know that explainable artificial intelligence, here machine learning really, is important. In healthcare, we can have applications where you cannot allow the AI to make any mistake. And in biology, you may want to learn complex interactions by looking at what the AI learned itself. So evolutionary computation, we believe, can be really helpful for this task. And in this work, we focus on symbolic regression by genetic programming. So GP has been shown to be very competitive in recent works when it comes to regression. And at the same time, we can exploit its parallel nature to obtain trade-off fronts of solutions where you have compromises between complexity or interpretability and your accuracy. And in real world applications, at the end of the day, you typically want to find a model that is precise enough and interpretable enough so that you can trust its use. The problem is that, like, how can we best define interpretability? So it turns out that in literature, there have been designed many complexity metrics, the simplest being the formula size L, you just count the number of components, but they typically focus on reducing bloat and improving generalization, not really on improving interpretability. So our goal was to make a step in that direction, trying to obtaining a better metric of human interpretability and try it out. And we like to quote reviewers too, saying that who said that our work can be best described by the haiku: when creating models by machine learning, create the indicators for assessing the models by machine learning. So what we did is we surveyed humans. We asked them to simulate, given an input, what is the output a formula is going to have, and we asked them to tell us how does the function the formula described change if part of it changes. And these are properties, simulatability, decomposability, that come from literature in explainable artificial intelligence. Given this data, we basically fit a linear model of interpretability of formulas, which looks itself like a formula, which you see here. So this is M phi, and it's based on some simple features that have to do with the size of the formula, but also with the type of operations going on and how they are concatenated together. And next, what we did is basically run a GP version of NSJ2 where the first objective is the mean square error, and the second objective is computed by literally plugging in this model M phi. And we compared it with with having a second objective, the formula size L. Okay, I show you now results for the dataset energy heating. We have 12 more datasets considered in the paper. What you see here on the vertical axis of these plots is the test mean square error, lower is better. And on a horizontal axis, also here, you go right to left is better. And in this case, on the left, M phi is computed as metric of complexity dash interpretability. In the case on the right plot, it's about L, the number of nodes, 3 nodes in GP of components of the formula. So the blue dots come from 50 runs, 50 fronts of this NSJ2 version of GP using our model. The red dots from the equivalent using L as second objective. So what you see is that the models that are simplest according to one metric are not the simplest according to the other one. So you may have models that are a bit longer, but are considered simpler because they don't have as many non-arithmetic operations and their compositions. And you see the same also when you look at more complex models and when you look at these distributions, okay? At the same time, what we find is that statistically significantly for most data sets, when we use our method, we are able to better reach lower areas of mean square error. So you see there are more blue dots here than red dots, both here and there. So let me go to the conclusions. So what we find is what I just said. What using our model instead of formula size seems to help reaching lower mean square errors. This is because we believe more diversity is maintained, and this contributes to evolvability, but we need to check this further. Second point, we argue that the formulas are more interpretable when we use our model. We do this by looking at them. And this will be reasonable because our model is fit based on human feedback. And finally, we expect that better models of interpretability can be built if we were to have more and better data. In our case, we had only a few respondents, 334. At the same time, we had this linear formula as a model, but it needs not to be. It could be, if we have enough data, a very complex black box neural network. All right, so thank you for your attention. You can find the code related to our paper at these links below. Thanks again. Cheers.